Welcome to lecture 11.1. Okay, so I'm going to start off pretty much the whole session. I'm going to talk about the Gross-Close-Crable paper. By the way, if anyone notices that I'm putting a whole bunch of my papers on the syllabus, some people think, oh, it's a sign of an ego. Well, maybe that's true, but the real reason is those are the easiest for me to understand, the ones that I actually wrote. So I'm biased toward that. So, and definitely this is true of this one. And as I said, the father of this type of analysis is Jonathan Feinstein. So ours is, you could maybe call it just a special case of his analysis, but the beauty of our paper, mine Grable's, is that it's easier to understand than the Feinstein paper. So, okay, if you recall, okay, I think I talked about this. A person in the House of Representatives, 1992, deciding to run for re-election or not. BI's the benefits of office. Okay, so you only get those if you win. PI is the probability of winning if you run. CI is the cost of running. I runs if and only if that's true. We just put some structure on this. B equals this as a vector of independent variables times beta. C, the cost of running is this. Then we say, well, okay, this probability term, we're going to get this from here. The I wins if and only if ZI delta. ZI is going to be some independent variables. Things like whether you've been redistricted. One was a key one was the House bank scandal. So some people, as I mentioned in last session, there were some people who bounced some checks from the House bank, and this was widely reported, and it was a very easy variable for voters to interpret. The journalists just published how many bad checks these different members of Congress had written, and so that was our variable, like how many bad checks you are. That should affect your the probability of reelection. Meanwhile, it shouldn't affect how much you enjoy the office or how much the cost of running. So it should all be in this PI term. So okay, so we got that, and then we get down to this I runs if and only this, probably I runs equals this, and then here's the likelihood function. Okay, so let me now discuss some of the questions that I gave in the Dropbox, questions to ponder. Okay, and the key is a lot of those questions to ponder, they're a bunch of them are just these counterfactual things. I'm reminded sometime in the 70s, maybe it's 80s, Saturday Night Live had at least one skit, and then maybe two or three. And it was called something like "What If" or something. It was acted like it was a PBS special where historians would gather and talk about counterfactuals. What if something had been true? And I remember one was, what if Superman had been a Nazi? What if Eleanor Roosevelt had the ability to fly, like during World War II? So that's what we're doing here. The beauty of an econometric model, some theory, so you can ponder those questions. What if? And I think this is especially true for these, I'm going to call them Feinstein type models, these detection controlled estimation models. And you can do some counterfactuals that sometimes seem like magic, I think. Sometimes you can do counterfactuals as just the normal econometric model, but sometimes the special structure of the Feinstein type models adds some stuff and makes it seem even more magical, I'd argue. Okay, number one, given your estimates of beta, gamma, delta, okay, given your independent variables of xi, Write your estimate of the probability that person I runs for re-election. Okay, it's pretty easy. I've written this. All it is we got this term. We wrote it. So xi, everywhere you had a beta, put a beta hat. Everywhere you had parameters, put a hat on top of it. That's all you got to do. Okay, so that's the probability that I runs. Okay, number two. Suppose I is guaranteed. Two. Suppose I is guaranteed re-election if he runs. That is P sub I equals 1. Write your estimate of the probability that I runs under this counterfactual situation. All you got to do is just take this estimate. That's the probability of winning. Just cross that out and instead it put 1. That's it. So for any person I, that's the probability that our estimate of the probability that he runs if he were guaranteed re-election. Okay, so that's the answer to 2. Okay, 3. Suppose all incumbents were guaranteed re-election. Given this, what's the expected number of retirements? Okay, this isn't that hard. It's just this estimate. So what you do is let's tell you what. Let's again, as I said, we omitted. I think it was exactly 13 people who either died or decided to run for the Senate. So now, I guess in this this counterfactual case, we're considering if you're guaranteed re-election in the House, maybe some of those guys wouldn't have run for Senate. But let's put that question to the side. So let's say of the people who were alive and didn't run for Senate, so that's 422 people. How many of those would have retired? Or let's see, how many? That's what's the expected number of retirements. Well, okay, first let's just see how many would run for re-election. And that answer is just the sum. Just add a summation. I equals 1 to 422. That's it. So that gives you the number of people who are expected to run for re-election. So the number of our estimate of retirements is just that 422 minus that number. That's our estimate of the number of retirements under this counterfactual. Okay. Now, number 4. Suppose that incumbent I retired, but suppose she were forced to run for re-election. What's the probability that she loses? Well, okay. If we have person I, the probability, our estimate of the probability that she'd win is just this term, phi zi delta hat. That's it. So our estimate of the probability that she would lose is just 1 minus that. Okay, so that's another thing we could say. Here's some counterfactuals we can run. Take any incumbent that retired. We can, from this great thing with a structural model, we can say, okay, here's our estimate of the probability that he or she would have lost if she had run. Okay, number 5. Suppose all retiring incumbents had instead been forced to run for re-election. How many more defeats would this cause? Okay, so a defeat, probability of defeat is just 1 minus phi zi delta hat. And then how many, so that's the probability of any given one. and then the total number, the total expected number, just equals, you take all of the people who retired. So I within, let's call it big R. Unfortunately, R also stands for ran, but the big R is retired. So it's 53 people. So you just take all those 53 people, look up their ZIs, their independent variables for that reelection, uh, that reelection term. Just multiply it by delta, take big phi of that. That's it. Okay, that is the estimate of how many more defeats we would have had under that counterfactual situation. Okay, that's number 5. Number 6. Suppose grandfathered cash did not exist. That is, no member had been allowed to convert his or her campaign war chest into cash. Okay, this question really doesn't take much advantage, if any at all, of this special model. The fact that we had a structural model, you probably do something like this with a logit. But the idea, all you'd need to do, let's get rid of that. All you got to do is just look at this, so that yi gamma hat, that yi gamma hat, that just equaled yi1, so that y is a vector, gamma 1 hat. I think maybe it's 3 variables. I can't remember. Y I2 gamma 2 plus y I3 gamma 3 hat. And I could say the first one represented that grandfathered cash. So we could look up with every member, every incumbent, how much money they had in their campaign war chest that they could convert to cash. And so it's only case, something like only 1/3 of them could do this with any money. But we said, suppose even that 1/3, all of their cash was 0. Well, all you got to do is just change that yi to 0, substitute that in there, and then calculate how many run given that, okay? And let's see, and what we do? So you'd expect, or I guess the other way, it's just put 1 minus phi. That's the number who retire. So just do 1 minus phi, sum that over all the people. I think you do all the members. What was the question I asked? Suppose the grandfathered cash. Suppose no house member. So this you'd sum over all 422 in the sample in that case. But all you've done is just changed one of the independent variables, set it to 0, and you see what you get. And we actually reported this in the paper. So this was in table 3. So there were 53 retirements, and then do this 4 different columns. Number 1 is where we assume both error terms are normal. I think 4 is where we assume both error terms are logistic. 2 and 3 is when we assume one is logistic, the other is normal. The kids, you get about the same answer every case. So I'm going to look at 1. So you get only 32 retirements. What you got in actual practice was 53. So our estimate is that if you got rid of the grandfather cash, do that counterfactual, he said, you'd have 21 fewer retirements that year. Okay. Let's see. How am I doing? Let's put grandfather. Okay, number 7. Suppose the house banking scandal did not exist. How many fewer retirements would there have been? Okay, for this one, all you got to do So the same thing. So before, all we did is we just took one of those yi's. So instead of using the actual value of the independent variable, we substituted 0 for everyone. You would do the same thing here. So this zi, the bank scandal, so the number of bounced checks for each person is one of the zi variables. So for this question that I just asked, all you do is just take one of the zi that corresponds to the bounced checks, just set it 0 for everyone, compute that, or I guess it's 1 minus that. That's the estimate of how many people would retire. Compare that to 53. Well, let's see. When you sum that, you get row 2, no banking scandal. So we get 47.5. So remember, 53 actually retired. So what's that? About 5.5. 5.5 fewer retirements if there hadn't been a banking scandal. Okay. Let's see if I can do. Grosskreutz and Crable computed their estimates before the election occurred of the incumbents who did not retire. What is Grosskreutz and Crable's estimate of the number who will win re-election? Okay. The great thing is, it's just this phi. The probability that they would win is just phi of zi delta hat. And in particular, what we might do, we'd say, well, that's for any one person, but let's look at the people. Let's see what I ask. Estimates of the House incumbents who do not retire. So let's look at the ones, I'm going to call it R bar. So R was the ones who retire. R bar is the ones who do not retire. And also remember, we've thrown out the 13 who have died or are not running for re-election. But that's all you got to do. Just sum that. And that gives a prediction. This gives an estimate of the number of people of the House incumbents who do not retire. So suppose just before the election, we know who's retired, who's not. We have 53 retired, 422 are in the sample. 422 minus 53, 369. I think that's it. So you'd sum this over the 369 people who are running for re-election. Sum all those probabilities, and that gives our prediction, actually, because we're doing this before the election. This is our prediction of the number of people who will win. And I don't think we reported that. I can't remember. I think it's pretty good. I think I would have remembered it if it was really off. Okay, so those are the 8. Okay. Let me do number 9. Let me do that in another. It's going to take a little bit of time, so I'm going to do that in the next, not session, the next part of this session. So that will be in 11.2. Okay, see you there.